to take a look at some review from last week. And last week we talked a little bit about machines. And of course, machines are essentially an example, I guess, of a machine. Well, a machine helps us to do work, okay? Helps with work. So it makes work easier. In some way, it makes, it leverages, and there's an interesting phrase, it leverages our work. So we put work into it, but we get more, using a machine, we accomplish more work with less effort. So the effort is multiplied by a machine. So as we think about some of the machines, we talked about different types of levers. And one of the levers that we looked at was this idea of a block and pulley, or a pulley system. So let's just draw ourselves a quick diagram. And let's say we have a 10 Newton weight that we're trying to hoist. And so it has a little bar there, and then we tie it to a rope and we hoist it over, and we're going to give it a pull. Okay? And so we can see that this machine is going to help us in a way. We can stand, for instance, in order to pick this up, we can pull this with our hands, and we can stand there, not bending over, and pull. We can even kind of hang on it with our weight. And so that helps us lift up this 10 Newton weight, this 10 Newton box. But we can also see that as I just have one pulley here, as I pull 1 meter, this weight is going to rise up 1 meter. Okay, there's no real advantage the way I've got it rigged up that it would be a mechanical advantage for me here. I'm going to pull 1 meter, and it's going to go up 1 meter. I have to pull, say pull is 10 Newton pull, to raise this 10 Newton box. So there's, energy in, I'm getting energy out. So the mechanical advantage of this is going to be, you can see the distance that the resistance is moved is 1 meter, and the distance that the effort is applied is 1 meter. So it's a 1 mechanical advantage, 1 to 1. Okay, so that's pretty easy to see. We also notice that the rope that the weight is on is just one rope. It's the rope that comes over the edge. It's just one rope that's being pulled up as we hoist that weight. Now let's look at a different situation a little bit. Let's look at a ceiling, and we now have a pulley, but now it's a pulley system. We've got 2 pulleys in tandem. Okay, and then down below, underneath, we have a weight, but it also has a pulley on it now. So the weight has a pulley on it, and the weight is, let's say 30 newtons. Let's say it's a pretty heavy weight. And we've attached now this rope. I'm going to put the rope in red, see if I can do that. Kind of get fancy with you guys. There we go. So the rope is going to go around this first pulley, and then down and around that second pulley, and up around this pulley, the top pulley, and this is the direction I'm going to be pulling it down. Okay, so we can see right here that the weight of this 30 Newton box is being, I guess the weight is divided over 1, 2, 3 different ropes. Okay? So the weight, as this box hangs, is over 3 ropes. Okay, now I'm going to pull 1 meter. Okay, how much will this box go up if the weight is divided now over 3 ropes? Well, it's going to rise. For every meter that I pull, it's not going to rise that much, is it? It's only going to rise 1/3 or 0.33 meters. Okay, so in other words, the resistance is going to rise 0.33 meters for every 1 meter of effort that I put. So here's my effort on this side. This is the resistance. The resistance will rise up only 1/3 of a meter. Okay, so I have to get this thing to rise way up, all the way to the ceiling. I've got to, let's say the distance is 3 meters to get it up to the ceiling. I've got to pull it 9 meters. Do y'all see that? Because my effort, every time I pull 1 meter, it's only going to go up 0.33 meters, 1/3 of a meter. So if this whole distance to the roof is 3 meters, I'm going to end up pulling 9 meters over here, see? Because, so I'm going to be doing more pulling, but here's the advantage. The advantage is the weight of this 30 newtons is also divided by those 3 ropes. So it's as though I only pull with a, let me change that a little bit. It's as though I pull with an effort of 10 newtons, okay, 1/3. So I have a 10 Newton pull. I'm raising up a 30 Newton weight, but I'm having to pull, my effort has to pull over a longer distance, okay? But I can do that, so I could actually see myself, if I could lift up a 600-pound block of concrete by rigging up enough pulleys, right? And so we would say the mechanical advantage of this pulley system right here is 3. And it's very, essentially, it's very easy to kind of remember that, in that it's the amount divided over the number of ropes. Okay, so the mechanical advantage is 3. All right. Yeah, so that's the advantage of using pulleys. So you could essentially rig up enough pulleys. I saw one guy do it. He had, I think, 10 pulleys. He had a 10 pulley system, something like that, 9 or 10 pulleys, and a rope that went back and forth, through the pulleys. And he had it attached to a car. So the car was, the car weighed about 3,000 pounds. And it was a good-sized car. And so a little kid came up and pulled the other end of the rope and could move the car just by pulling that rope, because the weight of the car was divided over 10 ropes. So it was as though you were pulling not 3,000 pounds, it was as though it felt like 300 pounds. And this kid could pull the rope and it would move the car. So it's pretty neat seeing how pulleys work. So let's define mechanical advantage. Once again, just to review, is the free multiplying effect or the free multiplying ability of a machine. So in other words, this machine is multiplying my work, my effort, 3 times. I'm getting 3 times because it's dividing the weight of the resistance by 3. It's divided over those 3 ropes. So what you do is you add up the number of ropes, and that becomes the mechanical advantage. Now, this mechanical advantage of a pulley, of course, can be used for doing lifting a load up to the top of a building. You know, you'd have building materials. You could have a guy down here on the ground, and he's lifting this, and of course he could do this. This is going to have a mechanical advantage of 1, right? Because for every meter he pulls down, the resistance is going to go up 1 meter. All right? So as long as he's heavier than this pile, these bricks or whatever he's lifting, gravel, he can lift that. You know, he can do that with 1 pulley. He could put it up 6 floors, right? So here's a true story. This is actually a form that was filled out a number of years ago, and I'm going to read it to you. This is true. I'm not altering it all. And here's what this person has written on this accident form. I am writing in response to your request for additional information. In block number 3 of the accident reporting form, so in other words, this guy had some kind of accident. Let's read about it. In block number 3, I put, quote, poor planning, unquote, as the cause of my accident. You said in your letter that I should explain more fully, and I trust that the following details will be sufficient. I am a bricklayer by trade. On the day of the accident, I was working along the roof of a new 6-story building. When I completed my work, I discovered that I had about 500 pounds of brick left over. Rather than carry the bricks down by hand, I decided to lower them in a barrel by using a pulley, which fortunately was attached to the side of the building at the 6th floor. Okay, so let's kind of get a picture of what he's doing. He's got a barrel up here on the 6th floor, so it's a little different than this diagram. Let's alter this diagram a little bit. Yeah. So he's up on the 6th floor doing bricks, okay? And so he's got bricks that he's working with on the 6th floor, and he has a barrel that's attached to the 6th floor. So let's go ahead and attach it. He's got a barrel. Come on. Okay, here's this barrel here, and he's got it attached to a pulley, and I guess he's loading it up with bricks, and he's probably got it tied to something down here. We'll find out. So he's got it tied to some object. That's not him standing there, but we know it has a mechanical advantage of 1, doesn't it? Okay, just because it has the 1 pulley. So he said the pulley, using a pulley, he had them in a barrel and wanted to lower this 500 pounds, okay, down the side of the building. Securing the rope at ground level, okay, so this was secured down here at ground level. I went up to the roof, swung the barrel out, and loaded the brick into it. Then I went back to the ground and untied the rope, holding it tightly to ensure a slow descent of the 500 pounds of bricks. You will note in block number 11 of the accident reporting form that I weigh 185 pounds. Okay, so he's down here. He's 185, but there's 500 pounds of brick up in this barrel that is now going to come down. So, can you see a problem here? Yeah. Well, let's keep reading. Due to my surprise of being jerked off the ground so suddenly, I lost my presence of mind and forgot to let go of the rope. Needless to say, I proceeded at a rather rapid rate up the side of the building. In the vicinity of the third floor, I met the barrel coming down. This explains the fractured skull and broken collarbone. Oh, goodness. Slowed only slightly, I continued my rapid ascent, not stopping until the fingers of my right hand were 2 knuckles deep into the pulley. Ouch. Fortunately, by this time, I regained my presence of mind and was able to hold tightly to the rope, in spite of my pain. At approximately the same time, the barrel of the bricks hit the ground, and the bottom fell out of the barrel. Devoid of the weight of the bricks, the barrel now weighed approximately 50 pounds. I refer you again to my weight in block number 11. As you might imagine, I began a rapid descent down the side of the building. In the vicinity of the third floor, I met the barrel coming up. This accounts for the 2 fractured ankles and the lacerations of my legs and lower body. The encounter with the barrel slowed me enough to lessen my injuries when I fell into the pile of bricks, and fortunately, only 3 vertebrae were cracked. I am sorry to report, however, that as I lay there on the bricks in pain, unable to stand, and watching the empty barrel 6 stories above me, I again lost my presence of mind. I let go of the rope. So the barrel came down on him. So this poor guy had a bad experience with a pulley system. So you have to be careful when you're using pulleys. Well, today we're going to pick up and study fluids. And sometimes this is called fluid mechanics because it has to do with how fluids move. And of course, fluids move different than a solid. In fact, in a fluid, all the particles of the fluid are in constant motion. And not only are they in constant motion, but they are in all directions as well. So if you think about air inside a container, the air is, exerting a pressure on the sides of the container, and so air molecules are moving. Same thing with water. If you put water in a plastic bag or something, the pressure of the water molecules have some motion, some kinetic motion, and so they're pushing against the sides of the container. So this motion is in all directions, and the force, or this is measured by, but as a force on one surface. So when we think of if we put water on a surface, let's say we have a surface, we drop some water, the water kind of piles up and sits there. Well, what would be the force of that fluid? It would be the force the water is pushing on that surface. So whatever the surface is, that's how you measure the pressure. So the pressure of a fluid is really equal to the force that it's pushing over an area, okay? It's a force divided by a unit of area. force divided by unit area. Now, the force is measured in newtons. Just like we measure the weight of those boxes as a force. And of course, the area will be in cubic meters or meters squared, right? So 1 Newton force on 1 meter squared over 1 square meter has a name to it. It's called 1 Pascal, and it's P-A, and it stands for a famous scientist, Blaise Pascal. Okay, so in other words, 1 Newton divided by meter squared is 1 Pascal. That's our unit for pressure, for fluid pressure. Now, air and water both exert pressure. And we can imagine that we know that as we've dived into a swimming pool. And the deeper that we go into the water, for instance, in the swimming pool, we have more pressure. And the same thing deals with air. So we know when we dive into a pool, the pressure increases. And that's because you have all this water. The deeper you go, you have more water pressing down on you. Okay? And the same thing with air. So if we have the surface of the earth, and we've got this atmosphere, okay, and the atmosphere is this blanket of air, it is pushing down on the earth. So at sea level, at the very where the beach meets the ocean, at sea level, we would have the highest pressure of air, right? We would have what we call 1 atmosphere of pressure. That's the pressure of air at sea level. They measure it in this thing called atmospheres. 1 atmosphere is equal to 760 millimeters of mercury in a barometer. So the barometer has mercury in a tube, and as you take it different places, the air pressure is a little different. At sea level, it pushes down enough that it raises the mercury to 760 millimeters in a barometer. And a barometer just measures air pressure. So let's go ahead. Baros means air, I believe, in Greek. So a barometer is the word for to measure that air pressure, or to measure pressure. Now, we also can measure it in bars. So there's another measure that we often use, and so hence barometer, as we measure the bars of pressure. Okay? So you need to know that at sea level, it's 760 millimeters of mercury, which is equal to 1 atmosphere. Now, obviously, here's Albuquerque. You know, we're at a mile elevation, roughly. About where Hoffmantown is about 5,600, a little bit more than a mile high. So guess what? The air pressure is going to be less. We have less air over us pressing down. Okay, so in a way, we could see that if this was, looking back at this very brief diagram here, the air pressure is, the atmosphere presses down. But here's Albuquerque. We're perched way up here near the Continental Divide. We're over a mile higher. So see, we have less air pushing down. So this is the continent of North America, and there's the Continental Divide. So we're about a mile high at that little X, and so there's less air pressing down. So we're not going to have as much air pressure. So for instance, if we're boiling something in a pot, and the water normally boils at what, 212 degrees Fahrenheit, right? Or 100 degrees Celsius, right? So we have less air pressure pushing down on us, so it's going to boil earlier. It's not going to be as hot, and it'll start boiling because the air pressure is not pushing down on it. It allows the boiling to happen at a lower temperature. So one of the things that we do when we camp out in New Mexico is if we take any water or drink any water, we need to sterilize that by boiling the water, but the water will boil at a lower temperature because we're at a high altitude. So you just have to boil it longer. You have to heat it up a little higher. Instead of just stopping when it starts boiling, keep heating it, make sure it gets all the way to 212 Fahrenheit to true boiling, and then it'll kill the bacteria and the organisms in it. Or if you're cooking, you have to adjust your recipe. You have to know that in Albuquerque, it's going to, the water and the materials in the recipe are going to boil at a lower temperature. So you have to take that into account. Well, we see this illustrated with water very easily, because if we put a can on a table and we punch a hole, and actually let's fill it with water first. So we put water inside the can, but we have a hole down here near the bottom, and then we put a hole halfway up. Well, if we punch the same size hole, water will escape and it'll squirt out. Okay? But if we punch the same size hole a little higher, there's of course less water pushing down on this at this level. So it's got less pressure, so it's going to go out, but the water won't shoot as far. This bottom hole, we've got so much water, the weight of the water in the can is pressing down, so it shoots out further. We can see that happen. So the greatest flow is at the bottom of the can. And that illustrates this idea that there's more pressure where there's more of the weight of either water or air. We can see that illustrated here with water. Now, Blaise Pascal came up with a principle that we want to talk about, and then we're going to go to our next part. He said changes in pressure, we're going to use delta, which means change, so change in pressure in a confined fluid, whether it's air or it's water, both of those are fluid, they both move, molecules are moving, right? But if it's a confined fluid, if it's in a can or some kind of container, the pressure is distributed equally. In all directions. So on one side of the can, the pressure is the same as the other side of the can. Okay? And we can kind of see that, especially as we've looked at something like a soccer ball. Here, a soccer ball, it's been pumped up, and of course the air inside is pressurized, it's pushing inside equally in all directions. Okay? So that's the critical thing to remember. It's equal and it's in all directions.